record on this computer. Okay, so welcome to this next session, and I will try to explain certain MATLAB tools. The file, the MLX file, which is a live MATLAB script file, and I can save it as a PDF file. I can share the code, so this is already uploaded. This time was early in times. So the point is that we start to, I mean, engineers would say, we go to the computer, and therefore we have to work with finite vectors. We cannot use functions. We cannot deal with infinitely many functions. Now, if I would give you a concrete formula, you would have, as a user, you would still have the question, well, how should I sample the function? If I say, well, the function is concentrated, so it has a support on some interval from A to B, and maybe it's a good idea to say, well, how many samples should I take? Sometimes people say, well, the computation of every single value is very costly. Then you might minimize the number of values. But then the function may oscillate a little bit, and if you take jumping, I mean, this large distance point is not so good. So essentially, the rough idea is, well, I have to sample the function long enough, wide enough, and fine enough. And we will discuss this in great detail or so. But roughly speaking, I would say, well, if you have a function and you want to do the Fourier transform, how do you explain what is the Fourier transform of a continuous function? And then the classical heuristic definition is that you say, well, if it was a function on the interval, so if it's a periodic function, so I take this function, wrap it around on the cylinder, then I would be able to expand it into a Fourier series. But now there is no period. Okay, let's assume it's more dense, more dense, more dense. And if you think everything in the continuous domain, it just says, well, you have these functions here, but by doing this zero padding or gluing this on a larger and larger cylinder, well, a cylinder which is huge is almost like a plane when you look at it, kind of tangent plane, so to say. Then you're getting more and more fine frequencies. So if you rescale everything, the big period, rescale the frequencies and say, well, in this interval, you have finer and finer information. So in the limit, you write integrals and you say, oh, I'm having all possible frequencies, e to the 2 pi I s xt for variable s. And then you recover in the same way by letting the inversion formula go to a limit or so. In our case, we don't want to do it to the limit. We just say, well, we think of a function which is mostly concentrated, ideal case, compactly supported, as something which is really copied in a periodic way, and it doesn't overlap. That's the first convenient thing. And then we are doing sampling. And what you will see by these experiments then later on is that sampling on the time side is periodizing on the frequency side, and periodizing on the frequency side and on the time side is sampling on the time side. And I've already mentioned this in the pre-discussion. What does it mean to periodize a function? It's twice, but to sample a function is to look at the function which is on the unit roots of order n at the unit roots of order n half. But you're going twice through them. So that's kind of, you will see this. Okay, so the point is, when we talk now about a function, and I'm having a kind of private or command, so many of these things that I'm doing now are not general MATLAB, but you will get access to the code, or so you should more understand how it works and how you can use it. So general recommendation when you write MATLAB code or you write your functions, don't use, or programming general recommendation, don't use function names which are too short and easy to type, or too long and easy to find, identify. If you have very long, you say, oh, I have to type in so much. If you take it too short, the namespace is too small, and after a while you don't remember and you have overlapping. So that's why most of the functions that I have, we try to keep a terminology that tells me already from the name what it should do. So FLT is for filter. So I will use it to filter a function, and it's S for symmetric. And in order to show you what it is, I'm showing you in trivial case a function which is placed on the unit roots of order 8. And I think you can imagine how this is working. So you have unit roots of order 8. Sorry, the 0 is here. So 1 is omega to the power 0. And 0 is the center. So if it would be a function on the real line, you would say the peak should be here. And I would like to draw a rectangular function which has a certain width. So if I say filter of symmetric filter of length n and width 2, right there, it's just saying, well, I'm in a discrete setting, so I'm sitting at 0. Well, this is this place. And I have 2 neighbors to the right and 2 to the left. So altogether, you see, of course, there are 5 ones, but it's an asymmetric way because, I mean, how should I put the numbers on the circle? You have to start somewhere. And the natural way, of course, is to start at omega to the power 0. But is it the first or the last? Well, that's a convention. We start here. And we say unit roots of order n start at omega 0, 1, and you go through it in the mathematical clockwise sense. So that's why you have 1. And the question is also, what is a function which is symmetric? And you would say an even function, and a Gerade function, is a function where f of minus x and f of x is the same. Cosine of x is cosine of minus x. An odd function, sinus of minus x is minus sinus of x. Yeah, what does it mean here? This function should, well, what can you say about an odd function? At 0, 0 is minus 0. So it has to be 0, like sinus, and the positive values and the negative values are on the left-hand side. So an odd version of this vector would be, you have 0 because you are at 0, and then you have +1, +1 maybe on one side, and you have -1, -1 on the other side. But the other side is the end. And that's, of course, not so nice to plot. So if you plot it, and you see here that this is the ordinary plot command, which has a few problems. And therefore I'm using the plot C command. And it's very easy. Maybe I'm showing. Oh, it's not. Yeah, I'm running it in the background. So the point is, the plot command, of course, says, well, this is a vector, and the vector starts with first, second, last component. Now, if you have 1, 1, 1, and then you go down to 0, you see 2 problems. One is that the frame is just your value is at the top. So I have a little command which is harmless, which says, well, make the axis a little bit higher to avoid this touching effect. I could maybe show you how this works. Ax20 is add 20% to the axis, which means the command is, sorry, this is typo. The command is, well, maybe I show you this command in the side window if it works, if it's not too slow. I don't know why it's so slow, but maybe the standard way of how I'm doing it is I create a variable name, and yeah. And the variable tells you, well, this plot in the active plot, that's not the one that we see here, is apparently, it has a left and a right and a lower and upper corner. So if you are plotting some function on the unit square, the axis will be from 0 to 1. And if it's a non-negative function with a maximal value 1, it will be between 0 and 1. So how do I do this command Ax20? I say, well, the signal length maybe is 200 or so. So maybe it's from 1 to 200, and from the minimum of the function to the maximum of the function is the usual display if you do axis tight or so. And I take this value, I take the range of the function, and I add 20%, means 10% below and 10% on top. So that's how you get this here. So then you see better the graph if it's here. But actually, it's better to center it. And the plot C command is putting everything to the center. If you don't put the labels correctly, then this is still labeled from 1 to 20, and then the values don't match anymore. So this is a kind of harmless, we shouldn't discuss the details of this. You can read it, the code if you want, but this is the standard way of plotting. And especially if you have a Gauss function. So think of a Gauss function put on the cylinder. So now my cylinder is going around like this. So if you look from top, so the peak, the Gauss function would be here. And the natural way of a plot would be cut it here, and you would see a bump function going down another. And of course, everybody would say, no, please, I look to the Gauss function from this side, so I cut the torus on the other end. And I put this and say, well, the first component was actually the value at 0. And so this is something that is very easy to learn. So this plot C command is something. So you see the stem command is just represent the values by needles, and the stem C is just doing the same centered. So you see it's a value at 0, 0 in the sense of omega to the power on the unit circle, and 2 to the positive values are going in the clockwise sense and the other in the negative sense. So this is a good display. You may say, I don't want to have the display in with, yeah, if I don't want to have the plot in this way, you see here there's another effect. You have the value 1, 1, 1, 0. The standard plot command thinks, well, probably I want to see a graph of a function. Have sampled the function, and you would like to have a piecewise linear interpolation. But you can also plot, of course, with another symbol. So you see K means black, and plus means you can plot it as singular things. Or the stem command, you can do it, mark it with stars and do it in red or whatever. So very often I will maybe show that the unit roots of order n are part of the unit circle. How do you plot the unit circle? I usually take the unit roots of order 720 or so, or 360 or so, and make a polygonal thing which looks as a circle, and then I plot, I keep hold on, and I plot the unit roots of order n extra. So this is a very harmless thing. Okay, and now I see I didn't do my standard setting. So kickfire is just a kickstart with where I create all my tools. I also have made sure that I could run code from the LTFA toolbox. There was some conflict of names, very few things. Usually conflict of names is not so bad unless you have two packages which allow the same kind of input but have different output. Sometimes it just doesn't work. So if you have a command which expects an image and you put in a vector, it says input is the wrong format, or so if it's well documented or so. Okay, so I'm doing now. Yeah, okay, so maybe I run the whole thing. Yeah, so one of the commands, or maybe I run it slowly. One of the commands I use very often, so again, or preview, the idea of Gabor analysis is to represent a function or a signal as a superposition of time frequency building blocks. So the best way to explain it to, let's say, even a high school student is also, assume you have a cheap synthesizer. So you can make tones like beep, beep, beep. So, and you do this at different times. So you can write a program that's saying, like the cheap synthesizer, I press an accord, so I'm having these things at the same time, and I'm doing this. So the idea of Gabor analysis is to have these elementary sound chip blocks, and the strange or interesting function space statement is of Gabor, if you have sufficiently of many, so you have sufficiently short interval so that your building blocks are overlapping, so there's not the gap and the big pause. And if you do it in microtonal way, which doesn't mean that you have 500 possible scales, but just sufficiently many so that even in the frequency domain, you can cover the time frequency span, then you can produce any sound. Or you can do a sound representation in a kind of a continuous way. So we were doing it discrete signals are represented in an even more discrete way. That will be the building block. And because Gabor himself was suggesting to take a Gauss function, if we are now in a discrete world, we should take the Gauss function. Now the question is, what is a discrete Gauss function? And I was already mentioning that you should think that it's just a coarsely periodized fine sampled function of the Gauss type. Now, if you want to introduce the Gauss function as a function, and that's another good trick that you should know, you can define in MATLAB with such a command functions of a variable argument. So clearly the name Gauss should be such that you have as a function of x, and the expression is the standard normalized Gauss function is minus pi times x squared. Now this dot before the squared means that you have input which can be a vector. And so if you want to see the size of the vector, then you can make the vector in format long, and then you might see that not really 0, but it looks like 0. But on the other hand, I mean, Gauss function at 3 is already extremely tiny. So there is a minimal number in MATLAB. Of course, we all know epsilon is a small number, so in MATLAB it's built in. It's if we ask is Gauss of 3 larger than 100 epsilon, so then it's still, yeah. So maybe we do now 4. It's just to test when can we safely ignore yeah, so I'm not doing it further, but the Gauss function at +4 is already in the range of 0 in the numerical sense. So if somebody takes a Gauss function and does a periodization with a period which is bigger than 8, the value at 4 is practically 0, and the next one at 8 is also 0. So you can ignore the periodization. However, if you're trying to take Gauss functions, I don't know, of size 16, then the fair way of getting 16 samples is, of course, to say, well, we all know 16 is 4 times 4. So let's the period before. So we take the Gauss function and the Gauss function. We want to center it at 0, sorry. So if 4 is the next neighbor, we look at it and sample it at a rate of 1/4, 1/4, from 0 to between -2 and +2. And then, of course, between -2, there is already an effect. So if I would, I could show maybe we can just do it, plot Gauss of, that's, I'm not doing it by hand, but the code is doing exactly this. It's taking more or less the period being square root of 24, or maybe I'm taking, I don't know, 64, then we know that's 8. So it's a period of 8 and sampling 1/8. And yeah, then we will see it in a separate window. Sorry that this will not be visible for the external people. Yeah, so you see something like this, but it's actually looking already good. So, I mean, only if you take a Gauss function of very small numbers like 12 or so, it will not look like a Gauss function. But if you have only 12 samples, it's not interesting anyway. Okay, so the standard difference, the standard plot would plot it in this way. You see it's cutting at 0, and the single peak value is at 0, and the next one is already at 1 over, in this case, 1/12. So you can imagine, yeah, Gauss MK. No, I was calling it G1444, and the second, well, at 1. No, sorry. Yeah, I don't want to play around. Of course, the norm of this function is made for different reasons. So the norm of this G144, so this discrete Gauss function is made such that it's normalized. For the short-term Fourier transform will be very useful to have normalized window, and you see the Euclidean norm of this vector is like this. So once more, how do I get this Gauss function? And the name Gauss NK is referring to the creator of this file, which was Norbert Keiblinger. So it's Norbert Keiblinger's Gauss function, if you want to. And we have other routines where different versions have initials of the generator. Okay, so it's, you take the function 144 is 12 by 12, you periodize it, period is 12, so it's practically not periodized. You sample by 1 over 12, and you start with the first component being at 0. 1 over 12, 2 over 12, 3 over 12, until you reach 1/2 of the period. Then you jump. I mean, you jump by reading the values. Of course, you're saying, well, now, well, let's say 144. What is 1/2 of 144? It's 72. I'm taking value at 0 and 1 and so on. So if I'm reaching 1/2 of 12, which is 6, I have already 73 values. It's now we have another side, and there should be another 73. No. This value is already here. So it's, this value is skipped. Then we go from the left side of the period and we start reading. And of course, the last component, because it's in the circle, should be the left neighbor. And then you have this situation. And then you get some bump function. And because for many experiments, the norm of this function is convenient to be 1, we always normalize it. Also, if I take a random vector, so very often we start normalizing it to make it easier. Okay, now I'm showing you the, okay, I have to rerun this selection. So if you are having any symmetric filter of lengths n and width here 20, of course it has 20 left, 20 right neighbors and 0, so it's 20 plus 20 plus 1 is 41. So it's just indicating how many. It looks like this. Now, another command which I'm using quite often and which is very convenient is to use this plot C command in a way that allows you to compare two functions. So F2SP is show two functions and their spectra. The spectra is just Fourier spectrum, is the Fourier transform. So if you want to compare two functions and you say, well, they look similar, are they really very similar? It's very often quite good, as you will see, to look at them in the time domain and the frequency domain. So we will discuss the Fourier transform a lot, but here you just see the Fourier transform of a rectangular function or boxcar function or a rectangular filter or ideal filter, because the engineers use these things on the Fourier transform side, and they would say the ideal filter is leaving out everything in perfectly up to this frequency, and then it cuts off. Well, if you look at the right-hand side, in this case, it's now, so the engineers would flip these first two plots or so. They would say, but in terms of real-time processing, it's not very good, because what you're doing is you're building, taking superpositions of this highly oscillating function. It's the so-called sinc function, the sinus pi x divided by pi x. So at each value where the sinus is getting the value plus or minus 1, the absolute value of this function would be 1 over x. So you can say there's an envelope like a hyperbola of this function, but because here we are not, I mean, we're seeing a segment of a periodic rectangular function. Therefore, you see here a sampled, also periodized function. So if you would look at the function sinc, draw a picture on the blackboard now. You would draw a hyperbola here. You know that the sinc function is 1, the classical sinc function, and then you will know it has zeros at the integers. So it goes down, sorry, and it has to go here and here and here. And I also have some demonstration that this function is not integrable, not absolutely integrable. Why? Because here you can put a rectangular box below here and below here and so on. So and this is roughly speaking of the order 1 over n. So the amplitude is 1 over x. This is at the point n. And therefore, the height is 1 over n. And we all know from analysis courses that we know that the harmonic series summation 1 over n is infinite. And the easy way to see it is you sum up from, I don't know, from let's say from 2 to 4. So what is 1/2 plus 1/3? It's more than 1/2 plus 1/2. Sorry. Let's say 1/3 plus 1/4. It's more than 1/4 plus 1/4, the last one. So it's 1/2. Then you say, well, if I'm already, I don't know, at 16, I'm saying 1 over 17, 1 over 18, and so on until 1 over 32. That's 16 terms, each of them of the size at least 1 over 32. Altogether, it's 1/2. And you can do this as much as often as you want. So this function is a bad guy from many engineers would say it has poor decay, but sometimes we will need filters which are better concentrated. And what is the purpose of a filter? Well, it's cleaning somehow. You want to have the main frequency should pass through and the high frequency should be killed. But we will see that if you're not doing this sharp and I call it pseudo-ideal cutoff, but you're doing it in a smooth way, you can gain a lot of concentration here. Okay, so now the next thing is the story about the Gauss function. The Gauss function is known to be one of the few explicit functions in a course on Fourier transform theory. You learn to compute the integral of the Gauss function, or in a probability course or so. And then you find out that then you prove that the Fourier transform can be computed explicitly with complex analysis stuff or whatever. Or as using differential equation, it satisfies some differential equation which is invariant with respect to the Fourier transform, whatever. I mean, but the Fourier transform of the Gauss function is one of the few cases where a function is invariant under the Fourier transform. Now, this gives you the impression, and that was, I would say, the state of the art for me as a PhD student probably. Well, there's very, very few functions which are invariant under the Fourier transform. Now, we will see that the Fourier transform is applied twice, gives the flip operator. Flipping twice is, of course, identity operator. So Fourier transform to the power 4 is identity. Oh, and we have Plancherel theorem, it's isometric. So, oh, that means all the possible eigenvalues have to be unit roots of order 4. So if you take L2, just as a story now, take L2, a quarter of the, I mean, yeah, there are 4 eigenvalues, and if things are fair, a quarter of these infinitely many dimensions must be invariant or so. And actually, you can prove that the Hermite functions are an eigensystem. And if you label them, the Hermite function with number 0 is the Gauss function, and then you have another collection of functions, and they are unit roots of order 0. I think, I'm not sure now, I think minus I, minus 1, plus I, and the Hermite function number 4, so the fifths in the system, 0, 4, 8, 12, they're all invariant of the Fourier transform. So if you take any linear combination of these Hermite functions, you get a function which is invariant of the Fourier transform. And there's a nice way actually to approximate a function by the nearest invariant function. What you're doing is, actually I have, something, sorry, that's kind of not prepared, but I can check if I have it available. Yeah, okay, so the code exists. I will maybe add it. The trick is very easy. You take the function, you take the Fourier transform, you take the square of the Fourier transform in the 3rd power, and then you take 1/4 of it. So if the function is invariant, you have 4 copies of your function. If it's not invariant, you get something which is obviously invariant, because if you apply the Fourier transform, it's like playing a carousel. Number 0 is 1, and so they're rotating and they are invariant. And so one has to prove. So this is an easy way, without knowing anything about Hermite functions, to approximate the function by the nearest Hermite function. So the point is, there are a lot of such functions, Only very few have explicit names. But I will show you some other examples which are quite easy. Okay, so what else? There is a text in the second plot saying that this is the unitary FFT, and if I compare a function and I want to show and demonstrate also with this plot that the Gauss function, its discrete Gauss function, is really invariant under the Fourier transform, then it's not good to take the ordinary function. So maybe I do on the side this small command, that I create a random vector, and Cn, it's another NuHAG command, so to say, private. It's random but complex, so it's C for complex, and N normalized. So I take real value between 1/2 and +1/2, or just symmetric positive and negative, or actually I'm taking random, which is 0, 1, and I subtract -1/2, and it's symmetric around 0. And the same for the imaginary part. And then I say, well, it should have the norm should be 1. So I would do this command. Now, if I want to know the norm of the FFT of this random vector divided by the norm of X, it's this, and in this side window, my standard signal length, which I use for a lot of experiments, is 480. And you see that, of course, always the same, that the inverse Fourier transform is the same as the forward Fourier transform, but in the discrete setting, our pure frequencies are absolute sinus and cosine, so complex value, so they have length 1. So the question is, what is the L2 norm, the Euclidean norm of a vector whose absolute entries are all 1? And then you say, okay, it has to be 1 squared, 1 squared, 1 squared, n, and then you take the square root. So every vector which is constant 1, and the pure frequencies are, it's better to keep this idea, pure frequencies are absolute value 1, even if they are discretized. Therefore, you have the FFT and discrete Fourier transform are having always changed the length. So I'm using norm of FFTU, that's a harmless code. That's kind of the unitary version of the Fourier transform. Yeah, so that's, maybe I also show you, yeah, no, maybe I'm just mentioning this. This FFTU command I don't have in the live script has 2 ways of usage. One is to say you give an input vector, and then of course you would like to see that the unitary version of the Fourier transform is applied, which means you take the forward Fourier transform divided by square root of n. What is the inverse Fourier transform? It's FFTU, but with a conjugate. What if you are saying FFTU of a number, then it says, oh, you're giving me a dimension. So I would like to get the matrix representing. So then you can play around and say, yeah, maybe we could do this here. Fu is FFTU of n. And then I could do B, and D is I of Fu. MATLAB is able to do, this is a unitary Fourier transform of size 480 now, no problem. Then maybe IQ is the diagonal. So the trick of this, or the point is, when you say that you have, what is the eigenvalue routine doing? You would expect you get eigenvectors and eigenvalues. But if you write it as a matrix, it's better to say, no, it's the eigenvalues stored in the diagonal matrix, because then you can say the product of the matrix containing the columns of the eigenvalues and the diagonal matrix in the right order gives you the same action as the original matrix. Therefore, this command is giving you a diagonal matrix, and I just want to pull out these values. Now, I don't want to show you all these eigenvalues, but maybe the first 6 or so of them. And you see, it looks very suspiciously like -1, -1, -1, plus I, minus I, and so on. So this is kind of computed in a more or less random order, but if you would plot it, I don't want to do it now because it wouldn't be recorded. You would just see it's just the unit roots of order 4 with certain multiplicity or so. And it is an interesting experiment, and was leading to a master thesis many years ago to say, well, what happens, what is the multiplicity? So if you take, that's a nice experiment that you can do yourself, take the unitary version of the Fourier transform of size 16, and you say, well, 16 is fair business would be for eigenvalues of dimension 4, but you will find out that it's 5, 4, 4, 3. So it's not exactly, but it's never deviating very much. So it's for certain numbers which are multiples of 4, I think it deviates a little bit to the favor of the, so there's a 5-dimensional eigenspace with eigenvalue 1 in this case or so. But that's, so going back to this live script, it's showing you that, yeah, maybe I should run this again. I'm doing this comp norm routine, and the comp norm routine is also something I'm using a lot to say, well, I expect that these two vectors, the FFT of my discrete Gauss function, it should be the function itself, but I also expect here, I expect already that it's not the same size. So it's clear now that the quotient of norms, oh, I just see, yeah, well, the routine has abstract input x and y. So it's comparing the norm of the first against the norm of the second one. So here the Fourier transform is the big guy who is 12 times, which is square root of 144, of course, times the size of the original one. But then it's normalizing the vectors, and then it's checking the difference. And this was extremely good when I was something computed in a complicated way, then I used FFT to do it in a fast way, and then, oh, I have to add a factor, and very often I just look at it, it's clear that must be square root of n, or here it's, yeah, square root of n in this case also. Sometimes, of course, you see not, you could see something not 12, but maybe you do things in you determine eigenvectors or so, and you might see almost 2 here. And then you would say, oh, probably I'm getting the right vector, but with a minus sign. So if it's in order to determine subspaces, that would be also okay. But I mean, here it's nothing like this. Okay, so the next thing that I would like to show you so there are two things that I will show with this command is how to create a two-dimensional Gauss function. I think I don't have to explain to you that a two-dimensional Gauss function is e to the absolute value of x comma y squared, which is of course x squared times y squared, x squared plus y squared, but in the exponent of an exponential function, so you can just split it. So what I'm demonstrating here is how can I create a function of two variables? So in a description, we would often write x tensor g as a function of two variables, and it's just f of x, g of y. So don't be afraid of tensors here. It's just a way to say tensor is a thing which depends linearly on each component. So of course the tensor of 3f with g is the same as the f times 3g, or it's resulting in the same function as 3 times the well-defined function f tensor g. So it's no problem. But in MATLAB, it's also easy to do. You're saying I have a column vector and a row vector. And if you do matrix multiplication of first the column vector with the row vector, usually I'm saying that matrix multiplication follows the domino principle. So you have a 3 by 5, it can be multiplied with a 5 by 7 matrix, and the result will be a 3 by 7 matrix because the 5 by 5 in the middle has to match, but it disappears. So if you're taking, I have no pencil here, yeah. If you take, also have to see whether you see it in the right way. If you multiply a row vector with a column vector, you would just, then the result would be one row and one column, so it would be scalar. You would say x1, y1 conjugate, x2 conjugate. So it's just the expression of a scalar product. So MATLAB doesn't have a separate command for scalar product. You just take the vectors and take the one which should be conjugate in the transpose conjugate position. So if you're a physicist, it's the first one, and here we're doing mathematics, so it's the second one. But unfortunately, the second one has to be put from column, I think we have two column vectors, has to put in the, so it's more like this. X and Y are coming here, and you have to put the Y, which is supposed to be conjugate, in the first position. So you have to compute in MATLAB Y prime with X, then you get the number. However, you can do it in the opposite direction. You can multiply column number, the row, or number. Then every entry is trivial. It's just x3 with y7 and so on, and you fill it. And you would say it's table multiplication. The table multiplication is just a discrete version of what we have here. So in theoretical physics, people talk about bra and cats. And you can say, well, this is just what you do in MATLAB. Starting from column vectors, there actually I have to mention that I'm using most of the time row vectors. This has, I would say, for me, many, for you probably some advantages and some drawbacks. So in linear algebra, you are used to have column vectors, and column vectors are handled. So you have a vector x, and the matrix comes from your side, from the left, and it's moved over to a of x equal y. So we are used to have left matrix multiplication. But you know the trouble that you have. Now I have two operators. First, I apply the matrix A, and then I apply the matrix B, and you have to pile it up. Yeah, and so we shouldn't start a discussion about Polish notation or so, but if you're saying, no, I have a vector X, which is a row vector, and then multiply, no, sorry, I have a row vector, and then multiply from the right, no, from your right. With a matrix, I'm doing linear combination of the rows, so of the rows here. So X has maybe X1, X3, X3, X1, X2, X3, multiplied with a matrix which has 3 rows, doing a linear combination of row vectors. Well, now you're probably confused a bit, which is the same situation that you have if you're flying to London and rent a car and you drive on the left. First, you're a bit confused, and after a while, you're knowing, well, everything is going in the opposite direction. Roundabouts are rotating in a different direction, of course, but on the other hand, everything is symmetric. And of course, you know how to take the transpose of a matrix. So whenever you are used to think of matrices applied to column vectors, I may write column vectors, row vectors applied under row vectors. The advantage is that the order of the operators and the order of the matrices is staying the same. That's one advantage. The second is if you have now 2 row vectors and you want to have the scalar product x with y, then you're saying, okay, it's x with y prime. And then the x1 goes with y1 conjugate. So that's my advantage. And in reality, the beginning was very naive. I thought, well, I have to deal with different signals. So let's look at these signals. So I'm thinking of a medical doctor looks the first signal, the second signal, and the third signal. So you put these, pin them on the wall, and therefore it was more natural for me to have routines that put all these signals, for example, the Garber functions in a matrix row by row, and have a command that shows you the first and second and third signal, and so on. The conflict that we have is, of course, that MATLAB, when you plot it, you have to turn it around because I don't want to change the plotting routine. And so sometimes it's a bit annoying or so. So now the question is, do you see anything? And probably if you look carefully, you see there are some little things here. And it's not even a Gauss function of big N, so it's small n. So I'm doing it to see better what's going on now with 12 and show you the standard display. So then you see we have the same effect as with the plotting routine. Interesting things happen at the boundary or so. But then my usual way of explaining it to you is to say, well, this is supposed to be something periodic. So you go to the market and construction market and you buy these tiles and then you tile your wall and And that looks nice. The only thing is, I show it here, that your tiles are here. So there is, I didn't want to spend time on plotting the separation lines between the different tiles or so. But of course, if you are saying, well, this is nice, the flower is in the center of the tiles here. It's not bad. But when I want to show it to you, it's better to take this image C command, which is kind of the analog of the plotting routine, putting the interesting part in the center, you see. And you also see here, it shows that 0 is not really 0. I mean, sometimes we were playing around and tried to make the cutting point. But here it's really better telling you, well, the entries in the matrix are this is the center. So any matrix, like a vector, has a first and a last component. Every matrix has a first row and a first column. And that's supposed to be 0, the offset. So if something happens, this light blue here is, or maybe we take this one here. This is, in terms of matrix coordinates, is the third row and the second column. Later on, we will say, well, it's for time frequency shifts. Well, this will be 0, 0, no shift. It's plausible to take horizontal movement as time shift, and this is frequency shift. So, well, we could try to do upside down, so an XY plot, but this is thinking we're doing discrete stuff, so we're having matrices. So the light blue contribution means, I will say, 1 time shift in this direction and 2 frequency shifts in the positive sense of frequencies, because positive means for me, if I'm hearing, if you do a continuous variable, it increases the frequencies. If I think of a discrete matrix, I'm increasing the row number. I'm going from row number 1 to row number 7 or so, which means I have to go down 6 more samples. So that's kind of this kind of transition that you have to learn. Now, of course, you could also say that such a function is a periodic function. And then you, of course, mathematically speaking, you are working on the torus. So we're having a function now which is on the product of a torus with a torus, which is a 2-dimensional torus. So do you have an idea of how it looks like? Yeah, it's a donut or a Schwimmreifen or so. And so what you are doing here is you're saying, well, I glue things together from this end, and I glue it together in the opposite end. And so if you want to go from here to here, yeah, I mean, I remember once, that's a story I'm always telling, once in the very early time of VAX workstations or so, the cursor was moving around in the matrix, but it was in a cyclic way. So if you were here and you wanted to go here, you were just walking across the North Pole and you were coming up down, and then you were walking to the right and you came in from the left or so. So kind of, because it was very slow to move pixel by pixel, more or less, the cursor, and the writing with ASCII code was, but that's exactly what you do here. So this function is, of course, a symmetric function, because the value which is to the right, to the left, is the same. It's much harder, or yeah, not impossible, but in a way not reasonable at the beginning to rotate a pixel image or so. Now, the next thing is a command which I call rot, and it's just shift in a discrete setting. So if you are having a function on the torus, it means that you're moving everything along the cylinder or so. So rot is just the command, and very often we have two things, which is one for applying the operator to a signal, and the other one is to create the matrix. So we have, sometimes we want to study a matrix doing certain things, so we would like to see the matrix which is doing the rotation, but first you just say, well, if you have a vector, you shift everything to the right, so if you do by 40, that's what you see here. The center of the peak is at 40 in this plot C command. Again, in the discrete, the data that would be, you would say originally the first component was the peak, and now you're moving it, so the 41st component would be the peak or so. Of course, if the code is correct, and you can try it, you could shift by -20 or by 760, and it would wrap around, and you would see modulo n in this case. Okay, the next thing is, yeah, if we create a collection of shifted Gauss functions, then it's done in this case by a for loop, because my discrete basis has 144 components, and clearly 144 by 9 is 16. So if I shift by 0, 16, 32, then I will get 9 different positions. And I was choosing a relatively large one so that you can see that, oh, it looks very much that they are quite separated. They're overlapping a little bit, but it's very plausible that they are linear independent vectors in this 144 dimensional space. So you have a for loop and you're plotting it. And here you see the need to, in order to plot it, I have to put my collection that are really separate signals in the transpose mode. Everything is real value, so the conjugate doesn't matter. Now, there is a command which I will use later on, which is translation basis. So if you have something with spaces, means I'm creating a collection here, a collection of functions obtained by the first input, which is the G, here the Gauss function of length 144. And how do you describe the lattice here? By saying how much do I jump? So it's 0, 16, and so on. There are two-dimensional versions where you can insert an image, and yeah, please. Pardon?
And I have a matrix,
yeah,
and I look through all the components.
Yeah.
And which one is the fast index? How is it?
Okay, yeah. So that is the row index. It's like a matrix, like a matrix. If you say A35, you have to think that's the third component of the fifth column. That's making it a little bit more difficult, but yeah, it's in this way. So maybe just as a test, T3 is how I'm doing my test matrix of size 3. Oops. Oh. Yeah, okay. That was a yeah, okay. That's not good. It was not serious. It should be 0, 3. So yeah, sorry. And T3, it was just stupid, can be filled with, this is the fill command, by any number. So now I know the running index or so. But I can also, that was your question, ask what is third row, second row, third component, and you will find it's this. So that's the first component. And for example, I could, that's another way which I find quite nice. Now I'm putting T3 of 1 to 4 to 9 is 1, 2, 3. So I'm saying I'm putting into the diagonal. How do I get into the entry? I have a full row, and then I'm at the position of the same, and then I add one more. So that's kind of 4 is of course 3 plus 1. And so I can fill it in. So it's just for a demonstration how the labeling goes. Okay, so since we have this, so this will be fine. Now, I will try to use the rest of the time to talk a little bit about determining a basis. So if it's true that these 9 functions are spanning a 9-dimensional space in my 144-dimensional space, I should be able to use it. Okay, there is a command which applies to any collection of vectors, but as I said, MATLAB is used to work with column vectors. Therefore, I have to create a collection of column vectors, and then I'm plotting them again. I mean, I want to have this orthonormal basis in the same format, but for the plotting, again, I have to do this transpose. You see they look a bit strange. You can try to figure out what is the first and second one or so, but I don't know exactly how MATLAB is doing it. I'm sure they are trying to be able to have an orthonormal basis even under not so good situations or so. So kind of a very fast, very reliable, very robust algorithm or so, but not useful for our purpose or so. Now, yeah, okay, so here I actually have show you some of these things. So I'm plotting them. Okay, so this is just plotting the original ones individually. Yeah, here you see it's at 0, at 40, at 80, and so on. So this is just because I was using this command, and now I'm showing you the result of the orthogonalization process. I must say it looks strange to me. I don't know how they do it. So clearly they are all smooth, of course, because they are linear combination of some shifted Gauss functions or so, but it's not clear how I do it. So how would you do it in a naive way? At the end of your linear algebra course, you would say, I have to apply Gram-Schmidt. Now I'm using a particular version of Gram-Schmidt more or less so that you can read the code. Because what is the idea of Gram-Schmidt? I have already done the first 20 dimensions. Then you give me the next linear independent vector, number 21. Then I would say, well, I have to project that vector onto this space and take the perpendicular part, normalize it, add it to my system, and make it number 1. And in MATLAB, the nice thing is I have already an orthonormal basis with 20 building blocks. So this projection is very easy. I take this, I take all the scalar products with these 20 vectors. Then I say, now I know the coefficients that I need to describe the projection. So that's just, I build my orthonormal system by adding one column after the others. And kind of the code of Gram-Schmidt is not many individual entries, but it's like three lines plus a recursion envelope. So that's more or less to show you. The point is now if you do this Gram-Schmidt, I also show you what the result is. And you see the first guy usually, and it depends on the labeling also. The first gets everything. The second has to throw away the part which is already covered. And you see after 2 or 3 steps, they look like translates of the original one. Yes, because there is no information about the future. The future is at the other end and comes only at the very last step. So you see the first, the second looks like almost, and then you shift it around, and the last is quite different or so. But they are not, and that's the point of Gram-Schmidt. Due to the big order, they are not shifted versions of 1. And so therefore, of course, the rank will be full rank, so that's no problem. Therefore, I'm suggesting to use the best orthogonalization, which is not so popular. It's known also as Löftin orthonormalization. And if I show you this collection, now ORTBEST knows already, the code is built such that it knows I'm starting with a collection of row vectors, and only for plotting I do this. And you see, oh yes, it looks like a Gauss function with a little negative bump or so. And let's see here. Yeah, I'm just plotting now the individual guy. But this is now a function which is composed from the original 9 functions. It looks very much like this here, but it's among all the possible functions, the function which is closest to the Gauss function, but still giving translates by the 9 an orthonormal basis of the same space. And now, if you play around, you can do this with Gauss functions which are more narrow and see how it looks like. And the more narrow you make it, the more things look like oscillating Gauss functions. So, and after having seen such pictures many, many times or so, I was able to get an idea. And the idea is the following. To put myself in a position that maybe the others can see. Now I'm in full light. So you have the Gauss function. And now another Gauss function comes nearby. You try to do something which is orthogonal, or maybe even first the bi-orthogonal system. So you have to say, no, they overlap too much. So I have to make a negative bump here so that the next one has a chance to be negative. And once you start to have a negative bump and you continue, then you need a positive bump and a negative bump and a positive bump. So that's kind of, if you put Gauss functions close and closer, everybody knows it's like having 5 vectors in R3. Let's assume I'm now in R5, but they're almost going in the same direction. So bi-orthogonality is getting more and more costly, more and more unstable or so. It's true, they are still infinite dimensional. If you give me any finite linear combination of 3000 Gauss functions in the continuous domain, I can demonstrate mathematically, analytically, they are linear independent. But if you do it in MATLAB, once you put them too close, once you have more than 144 in the 144 dimensional space, they will be linear independent. Yeah, and even the condition number is blowing up. So it's kind of, and the idea of this Lövdin orthonormalization is, yeah, maybe I'm showing you this. If you try to, I mean, what is an orthonormal system? That's the columns of a unitary matrix if you're in the n by n situation. So what is, and then the matrix is unitary if and only if this system, the basis is an orthonormal basis. So I'm asking you, if you are taking 1 by 1 complex matrices, and you will answer, we're talking about complex numbers. So, and you have some non-zero set in the complex domain, which is 1 by 1 matrices. And then you are looking at the unitary 1 by 1 matrices, then you will say that's the unit circle. Now I'm asking you, what is the closest in the sense of the Euclidean norm of set closest point on the unit circle? And then you will say, well, I have to draw the line and do the polar decomposition. Every complex number is a rotation plus a stretching. Leave out the stretching. And that's really what you can do. Now, if you jump and if you go to linear algebra, then you have a matrix A, and you can write it with the singular value decomposition as U multiplied with a singular value, which is more or less a diagonal matrix with a V prime. Now, what does it mean? That the action of A, the matrix action, can be decomposed into 3 things. So I should mention that these are 2 unitary matrices. So essentially, it says, well, why prime? It says, well, I want to describe the linear mapping from Rn of Cn to Cm. So what you have to do is the following, if you know the U and S and V. Take an orthonormal basis named V1, V. Then you take the coordinates here, V1, V2, and so on, scalar product. And then you say there's another orthonormal basis from the target space, it's the U vectors. And you just take the vector V1 and put it to S1 times U1. And so this way you can do it. So you can say every matrix can be written in this way, or you can also write it as U as U prime. Now, of course, I have to yeah, okay. If it's an n by n matrix, yeah? And then you're saying U with V prime. Okay. So I'm rewriting the matrix as this is a pure dilation matrix in the U system. So you have your coordinate system U, and you just stretch in that coordinate system. But what is now U multiplied with V prime? We know if you have a unitary matrix, the transpose conjugate is also unitary. The composition of 2 unitary matrices is also. So this is a pure unitary matrix. So throw out the dilation part and you get this. So the orth best is really more or less this code. Call the singular value decomposition and take the 2 bases together if it's an infinite situation. And what does it mean? Now, how do you measure closeness of matrices? Well, you're saying in the functional analysis course, you would take the Hilbert-Schmidt operator norm. what is it? As that the trace of A as a scalar product of matrix A with B is trace of A with B prime. You compute A with B prime, and then you're throwing everything away and just add the diagonal term. It's much better to say, well, in MATLAB, you can see it directly. A matrix is a vector in R9, more or less, if you read out individually. So you're in the complex Euclidean space of lengths n squared. And take a scalar product, natural scalar product that you would take if you would compare pixel images. The sum of the squares of all the gray values of the pixel. That's the Hilbert-Schmidt norm. And that you can do here. So now the point is, how can you interpret it? And I find it very, very nice, and I have to demonstrate it. If you're starting with an orthonormal, with a general basis, so you know they are spanning the R3, then what is an orthonormal basis which might be close by? Well, you think the angles they're too narrow. You are stretching them a little bit more. And that's what you actually get. Now, the good thing is with this construction is, well, what if I change the labels? I'm not saying 1, 2, 3, but I'm saying 1, 2, 3 in the opposite order, starting. That's a geometric intuition. So more or less you could say, this is the solution to a very natural problem. If I'm starting with 3 vectors which form a basis, and I want to modify them, I try to minimize the change. So I have to measure how much do I move the first one, the second one, and third one as Euclidean vectors. And then I'm saying, well, now I have 3 measurements, how much I have to move. And then I take the Euclidean norm of these measurements. But then you see, well, I'm doing just this Hilbert-Schmidt norm or pixel norm first column-wise, then I take a square root, but then I take the sum over all the columns, I take again the square, and then I take the square, so it's exactly the Hilbert-Schmidt norm. So it's not so trivial to verify that all this is true, but I think the intuition, if you have two vectors in the plane, you say, okay, they're just 60 degrees apart, take the middle line, stretch them, make 45 degrees, that's what you get here. If you're doing this ORT-best to these shifted versions, you can get this here. So the abstract way is to determine the Gram matrix and take this Gram matrix, which is a positive definite matrix, and take the square root of the Gram matrix. So that's the trick that you can learn in the Wordlet book of Yves Meyer for this situation or so. But at the end, it turned out that I was asking myself, why didn't I learn this much earlier in a linear algebra course or so? And I think it's one of the useful things. Okay, now we are close to an end, and I would like to show a few little things. We have, of course, a rectangular filter. Yeah, please. Yeah, we have a rectangular filter, which of course has to have 2 dimensions. So I'm creating a matrix of dimension 60 height for 80 width. And I have now in the row direction, I have 5 pixels. So it's 11 pixels, 0 plus 5 above and below. And I have here 12, meaning 25 in the other direction. So it's, and there's this centered command. And of course, it's the same as a tensor product of 2 rectangular filters. So this is just showing you it's really the same problem. It's even the identical code. It's taking the first one in the direction of rows. Why? Because you describe matrices by first row index, column index. So that's sometimes one has to be careful with when you think of functions. You would like x, y directions, and things might be, but here we are in a discrete setting. Now, what is rotate in 2 dimensions? Of course, it has to rotate rows and columns, and you have to have some convention. Do you rotate, and I always have to check it myself, do you rotate the rows by changing the row numbers or rotating in the direction of the row vectors? I think that would be 2 different. And first, but here I was, yeah, I'm doing this same filter by 18 and 11, and you see the first argument, 18 is the bigger one. I'm moving more, and I'm first moving in the direction of row numbers. I'm changing row numbers in a cyclic way. You can do it larger, then it will comes up from the top and so on. And yeah, this is just the test matrix. What if I do a rotation by 2 and 1 of the test matrix? My 1 point of reference is moving down first by rows, namely 2 rows down everything, and then rotate everything cyclic way. Each column is rotated in that direction by just 1. So that's why you have 1. And so it's just showing you the effect of these commands. Yeah, this is maybe takes a little bit longer, but I have already shown this to you. This is unit roots can be plotted with numbers or with stem. Stem now on the cylinder. I took a very tiny example or so. Yeah, okay, so well, it turns out my timing is better than expected. So I think that at least I have done what I have prepared, and I think it's the best moment to stop the recording. Thank you for your attention, and